Okay, so before we get started with this lesson, we're actually gonna talk about future lessons. So, as you guys might know, Cybersecurity Club here at Walnut competes in CyberPatriot, and some of you guys are actually in CyberPatriot or trying out for CyberPatriot. And so, if you guys are trying out for CyberPatriot, stay back for a while. So after we finish the lesson, we'll talk more about it. But after this computer networking lesson, we're basically going to be kind of pivoting towards CyberPatriot and focusing more on its aspects. So like next week's lessons will be on the Windows operating system and a lot of the CyberPatriot related information. And basically, the idea
Wait,
is, yeah.
wait, are we gonna do cyber breakout rooms instead?
Oh, psych. Oh yeah, we're gonna do cyber. Okay, but yeah. So we'll be focusing more on CyberPatriot. If you guys don't know what CyberPatriot is, there's a couple lessons on our YouTube channel. If you search up like Walnut CSC on YouTube, our channel will probably pop up, and you can watch them. But yeah, so we still recommend you guys to stay and learn along, but it'll also be additional prep for our CyberPatriot teams so that we can do well in competition. All right, so I think that's about it. You can put them in chat or something, but we'll go ahead and get started with the lesson now.
So I guess I'll start off. In case you guys didn't see the title slide, which we're going to be talking about computer networking in this lesson. So first off, what is networking? So a computer network is roughly defined as an interconnection of multiple devices, also known as hosts, that are connected using multiple paths for the purpose of sending/receiving data or media. And in computer networks can also include multiple devices, which are known as network devices, which we might cover a bit later. But those are things that are such as like a router or a hub or like a switch. And basically, networking in general is just the communication process between computer systems that are linked or networked in an attempt to share information or resources. And we'll explain more about networking and the computer network systems by using the OSI model, which Mr. Max will start talking about roughly now.
All right. So whenever you have computers on a network and they're sharing data with each other, they need to be speaking the same language. They need to understand what everyone is trying to say to each other, right? Now, just one note, when I say speaking the same language, I don't mean programming languages like Python or Java. That's higher level. The stuff we're dealing with right now is lower level, so it doesn't even deal with that. So back when computer scientists first made all this stuff, they made blueprints for all of these languages, all the ways that information would be shared between devices. And each packet of this information is what's called a PDU, a protocol data unit. Oh, sorry. Also, by the way, these blueprints are called protocol suites. I apparently forgot to say that. Uh, And so all of this data needs to know certain things. One example is where it's headed, the destination. And the protocol suite essentially states where all of this data will be placed within the packet. So maybe you have the destination at the beginning, and then the actual string or whatever you're trying to send in the middle, and then whatever at the end. It basically labels where everything goes in the packet. Uh, Now, all of these suites, am I saying that right? Okay, anyways, all of these suites are derived from the OSI model. The OSI model is a theoretical representation of what each one of these suites should do. One of the most popular of them being the TCP IP model, which we will not be getting into because we like to stick with the OSI model for teaching and for deriving new ones, since these 7 steps that you see on the right here, they detail everything that a protocol suite needs to know. And then one example is the client server model. So like, for example, when our computer asks for data from the internet, we send a request to a server. The server then compiles a PDU based off of the HTTPS protocol, and then it sends that back over to our computer, where the host computer, the one we're using, does the does the HTTPS protocol in reverse. So basically, OSI is just a theoretical representation of what these suites should be.
So the OSI model, layer 7 is sort of like the outermost layer. It's where application and user interaction takes place. Everything at this layer is application specific, and this layer provides services for file transfer, email, and other network software services. And some examples of this are like web browsers, Google Chrome, Firefox, Safari, etc., and Telnet and FTP. And these are examples of communications that rely on layer 7. Layer 6 is the presentation layer, and it represents the area that is independent of data representation on the application layer, which is layer 7. And this layer presents data for the application. An example of a presentation service would be conversion from an EBCDIC, a coded text computer file, to an ASCII coded file. And there are three main tasks done in layer 6 of the OSI model, namely translation, encryption, and compression. In translation, it acts as a translator between different data formats. Decryption is also handled at the presentation layer. For example, when logging onto a bank account, the presentation layer will decrypt the data as it is received. The final task of layer 6 is data compression, which reduces the amount of data needed for storage or transmission of information. Some examples of presentation are HTML, doc, JPEG, MP3, AVI, and sockets.
I think you're muted, by the way.
Shoot. So yeah, after the data is sent from the application layer down to the presentation layer where it's formatted properly, it gets sent down again to the session layer. And what the session layer is going to do is that it's going to use the layers below to establish a connection to the server or to the whatever remote device it is trying to communicate with. And it's going to establish a session. And a session is basically a temporary dialogue for data transmission. So if you want to talk with some device, a host, you establish some sort of session abstractly, and then so that it allows you to talk with multiple endpoints, multiple hosts at once, because they're all distinguishable because they all have different sessions. And one thing the session layer does is that it combine and synchronize data from different sources and send them like in a proper way. So for example, in a web conferencing app, you want the audio, what the person is speaking, to sync up with the video, the person who is talking, right, in the video. And you want the audio and the lip movements to sync up. And to do that, the session layer protocols is going to properly combine the audio and video and send them out at once. So and so so after session layer combines the data and before that it also creates a session, right? And then after all of that, it's going to send the data further down into the transport layer, and then which we'll cover it next. So now you have some data that you want to transfer, right? So basically, the client, it is you're on the left, and then the server, like google.com or something, or YouTube, whatever, it's on the right. And what you want to do is you want to connect to the server first, and then the server is going to respond with with that. It knows that you're trying to connect it, and it's not acknowledging it, and then it sends a response back. And then now the client knows that you've just established a connection, so it's going to respond again to say that it acknowledges the server's acknowledgement. Yeah, so this is the three-way handshake that from TCP. So this is roughly how communication works in this layer. So in this layer, the two hosts are actually talking. So from layer 7 to layer 5, it's all on one machine only. So but in the transport layer, we're actually acknowledging the existence of the other machine. So after connecting through this handshake, you're going to divide the data that you received from the upper layers. So imagine you're trying to send a 1 GB zip file. So how are you going to do that? Are you going to just send this whole big chunk of data at once? No, because what if something fails, like this package accidentally got corrupted, or if this packet, or if some network error was what if some network was not functioning well, and then this file got the transmission got paused. So what do? Well, it turns out that we don't want to send this whole thing at once. Well, what we want to do is that we should divide this file into little chunks, and then these chunks are what the PDUs are. So the protocol data unit are these little data chunks. They're usually about a few kilobytes or 1 kilobyte large, and then although the max is like 64 kilobytes for the TCP for transport layer, I don't think it's gonna get like that large because of the lower layer limitations. But that's going. I'm divert. Um, so so after you've divided the data into these separate chunks, you're going to choose one protocol according to your needs. So here we have the TCP, and then we have the UDP. So for the TCP, or the Transport Control Protocol, I think the PDU for this protocol is called segments, and the TCP protocol is connection based. So you try to establish connection, and then also have a reliable data transmission. So whenever you want to send like exact copies of the data, and you want the receiver to like fully receive it as is, you want to use TCP. It also has controlled. It also sends data at a controlled rate so that the receiver can receive it properly, even if it's slower than the sender. So it also uses techniques like windowing and stuff, but we're not going to cover it here. And in comparison, we have the UDP, which I forgot what it stands for, but we don't really care. And the PDU, the protocol data unit for this protocol, is called datagrams. This protocol is mainly used for real-time data transmission. So for example, if you're in a web conferencing app, you don't care if the other side or the other users received all of the the video or all the frames of the video that the participants are sending, right? You only care about in other words, it is okay if you don't if you only receive a part of it, so that you can see even though you dropped frames, you can see other people's faces. So you should use UDP if you want to just send the data as fast as possible, and you don't care about if the receivers actually receive everything or not, as long as they receive some of it. So for UDP, the speed of transmission is larger than accuracy, and for this reason, we say that we use UDP for real-time data transmission. And By the way, so for layers 7 to 5, we don't care about we don't care about the other host. But from this layer down, we actually are acknowledging the existence of the other host, and so that's why you have the PDUs, the protocol data units, to ease the transmission. And we also have a different name for so we have a different name for the PDUs for each layer, and because each layer needs to know some data about the host, but it doesn't need to know all of it. For example, for this layer, we need to know the port number that we are going to send the segments to, or the datagrams to. And for layers below, like network, we're going to need to know the the IP address, and for even below, we need to know the MAC address. And but we don't need to know all of these at once. So each layer is going to have its own piece of data. And when we send this layer's PDO down into the lower layers, that lower layer isn't going to care what the upper layer sent down. It's just going to package it, wrap it around with some additional data like IP address or MAC address, and then sends it down to the layer below. So okay, let's return to ports. And so ports are an endpoint that that some remote computer can connect to. And typically you can, so an operating system provides ports for processes or running programs to listen on. So or they can send data through the port as well. So if you have a web server listening on port 80, some remote server can send data to port 80 and then request the web server to send something back. And basically, this ports allow multiple programs to communicate over the communicate over in the same machine over the network at once. So some common ports are port 80 for HTTP, and 443 for HTTPS, or 22 for SSH. There are a bunch. You can probably check it out at c/services if you're on Linux, or you can just Google it.
All right, okay. So now moving on to network, this is more of a physical layer, and the previous layers, Zenkai's and the 4 to 7 were higher level, and they're within just the computer, and just now starting to get into the actual physical aspect. And so for network, we're actually talking about connecting between two computers on two different networks. And for this protocol data unit, it's a packet, and a packet is just a name for it. If the other ones have their own names as well, like a frame or a bit or those kind of things, or not a bit, but so for networks, we are connecting two different computers on two different networks, and we're trying to find a route. And so most of you guys probably live in a house with a router, I assume. And with your router, these routers basically connect. These routers route data, so they go from destination and they kind of figure out what's the best path. And by the way, Zenkai, you're unmuted. But these routers, they might go through multiple networks as well to get from one place to another. And so you have these, and in this layer, you have these IP addresses. So you guys probably have heard of it before, some way or another. And it's basically like the address of your computer, like how your house has an address, or how your house has an address. And so these, we have two versions of IP addresses, IPv4 and IPv6. Basically, IPv4 was created like in the 1970s, and it only had 32 bits, so it couldn't hold that many addresses. So as we got a lot more computers, it turned to IPv6, where it holds 128 bits now, which is a lot more, and it'll take a lot longer for us to use up. And so the main takeaway from, let's talk about DHCP and subnetting. So DHCP stands for Dynamic Host Configuration Protocol. And so when you have these IP addresses, you kind of have to figure out who is getting what IP address and how, and this DHCP basically helps different networks figure out what their IP address should be so that they can communicate with another network. And so with DHCP, you can computers are able to communicate to other networks, and subnetting, or that's the main idea of DHCP. So it's dealing with IP and making sure everyone can connect. And subnetting is basically the process of when you're going down levels. Let's say you're like you can see on the left, there's 172.16.254.1, and so every time you go through 8 bits, you're basically going into another level below, and it's like kind of a sub network. So you're going down in sub networks, and you can imagine if it's like you can imagine. You can imagine like you can imagine like a city although IP addresses, you guys might sometimes correlate IP addresses with location, but that's actually only a rough address estimate. And so that's kind of based off the sub networks. And so those kind of so when you go like try to track down where a guy lives in an IP address, it won't be that accurate because it's only giving a certain area. But subnetting is basically like you can imagine. I'm trying to think of it. You can imagine if there's like a college, a huge college, and then each department has its own subnetwork, and then within those subnetworks, for individual people, they might have their own like their own network, and maybe small groups will have their own networks, and eventually go to the individual computer. So yeah, so the main takeaway from network is it kind of creates this route, and routers create this route to figure out where to transfer data from one area to another and how it's going to get there. And it's more on the physical aspect, unlike the higher layers. All right, next slide.
All right, so data from layer 3 will then be transported onto layer 2, the data link layer. And this layer operates on the local area network because bits of data have already been transported by the network layer into the LAN. And the data link layer focuses on moving data into and out of the physical link of a network, which is the level below. And the data link layer is divided into 2 sublayers. One is the logical link control, or LLC sublayer, and the other is the media access control, or MAC sublayer. And the role of the LLC sublayer is to control data flow among various applications and services, as well as provide acknowledgement and error notifications. The LLC sublayer can then talk to a number of MAC sublayers, which control access to physical media for transport. And the MAC layer is then going to be responsible for moving data packets to and from one network interface card to another across the shared channel. 2 common MAC layer types you might have heard of are the Ethernet and the 802.11 wireless specifications. And one of the main functions of the data link layer is framing the stream of bits received from the network layer into manageable data units. The next step of the layer is to add a header to each frame in order to determine the physical address of the sender or receiver of the frame. And after that, a flow control mechanism is implemented to avoid congestion. And it accomplishes this by buffering the extra bits. This prevents a traffic jam from occurring at the receiver side. And at the end of each frame, error control is accomplished by adding a trailer at the end of each frame. This mechanism also prevents the duplication of frames. The last function of the data link layer is access control, and protocols in this layer will determine which devices have control over the link at any given time when 2 or more devices are connected to the same link. And this will provide like any unnecessary frame collisions, so like a car crash, and this will like ultimately slow down the entire network if they continue to occur. After all of this is done and the data is received successfully, the data link layer will send out an acknowledgement frame notifying that the network layer that everything is good and all the data is intact. Next slide. The physical layer is the lowest level of the OSI model, so think of it as like the ground level. And data in this layer consists of a stream of bits, which are then encoded into signals for transmission. Thus, this layer is responsible for sending bits from one computer to another, but it's not concerned with the actual meaning of the bits. That was the job of the higher layers that we talked about earlier. Here, the physical layer defines the rate in which bits are transmitted in the number of bits per second. So those are like its units. And it also synchronizes the transmitter and receiver. For all of these bits to be transmitted, there needs to be a way for the signals to be actually sent out. And this is done through media, physical media. There are 3 main types. The cheapest but also an effective way is the use of metallic or copper cabling. And data gets encoded as zeros and ones through electrical impulses. And the next is fiber optic cabling. The method is a lot more expensive, but it's also harder to implement. But all of it is off because fiber optic is a lot faster because the data gets encoded as light pulses and light moves really, really fast. The last method is wireless, which is most convenient, and data gets encoded as wavelengths in the electromagnetic spectrum. Next slide. And now you may ask yourself, how should networks be built and in what way so that they're reliable and good for customers? And 4 important factors come into play. The first is fault tolerance, which is how well a network can limit the impact of an outage or failure. In order to make the network fault tolerant, it needs to be built in a way that allows for quick recovery when such a failure occurs. And this can be achieved through redundancy, which uses multiple paths to a destination as a backup. Redundancy can be implemented by using a packet switch network where traffic is split into packets. So like, for example, if you're streaming something on Netflix, the data will be broken into multiple message blocks. The second factor is scalability, and this is necessary because as more hosts are added onto a network, space needs to be made for them without impacting the performance of already existing users. And networks are scalable because network designers follow accepted standards and protocols such as TCP/IP, model that we talked about earlier. And when everyone follows these sets of rules, it basically just makes communication and integrating all these different networks a lot easier. The third factor is quality of service, and QoS is a way for managing congestion and ensuring reliable delivery of content to all users. Congestion occurs when simultaneous communications across the network increase the demand of available network bandwidth, and the resulting demand exceeds the amount of actual bandwidth available. When the volume of traffic is greater than what can be transported across the network, devices hold the packet in memory until resources become available to transmit them, but the entire network still slows down. And the last factor is security, because data is crucial and personal or business assets have to be protected when important data is being transferred over the network. And this also relates back to the CIA triangle, which consists of confidentiality, integrity, and availability. So all 4 of these factors that we talked about have to be balanced in order to create a safe and efficient network. Next slide.
All right, okay, so now we'll talk, since we talked about all these layers 1 to 7 and kind of how the internet works with this OSI model, we'll talk about like the security part because we're a cybersecurity club. So we kind of broke it down into the 7 types of layers, but 5, 6, and 7, the more application side layers, kind of just got clumped into one because you know, they're pretty similar, and so but they still have their differences, of course. But so the first type of attack at layer 1, which is it's the physical layer. So you see a lot of stuff like where signals are getting sent, and there's a lot of things where there's signal interception. So you just pick up those signals, you try to process it, and you try to kind of gain information off that. And sometimes these signals are not encrypted, sometimes they are. And sometimes even when they are encrypted, you're still able to kind of decipher them if there's a pattern, or if you're able to detect some kind of pattern. There's even like machine learning with those kind of things. And another type of attack is signal jamming. So you can imagine this is actually pretty common in not just computers, but even something like there's a car and you have a key and you try to unlock the key, and someone actually takes that signal that you're emitted, and they're able to replicate that signal, and with that replication, then they can use that signal to unlock a car. And there's of course there's been work to prevent these kind of things happening. And so with the defense, there's usually a strong encryption. If you have really strong encryption, they can't figure out what your signals are sending. And there's still some kinds of difficult solutions, because sometimes there's signal jamming where they don't care about the signal that's being sent. Instead, they just want to stop your signal from being sent. So you can imagine if someone, you can like imagine a movie, right? So you need to call somebody and it's like some super intense scene, but then the bad guy signal jams your phone signal, so like that you can't even call it. Or even in worse situations where it happens in real life, where someone's trying to call 911, but their signal gets jammed, and so they can't call 911. And so that's kind of a layer 1 physical attack. Layer 2 attacks are on the data link layer. And so this is where, since you're working with a network, you can have things like MAC spoofing, where you pretend to be another computer, and there's man-in-the-middle attacks. And okay, so for a man-in-the-middle attack, basically what happens is, oh shoot, all right, hold up. Okay, you can just Google those. I kind of blanked out, but it kind of works like how it sounds. So there's probably some the guys intercepting a packet or data among a network, and instead they take the data, or they here, I'll figure it out soon. All right, but so for these kind of defenses, and DOS is denial of service. So for these kind of defenses, it's really just making sure your network's secure, your network's private, and your employees are knowledgeable and not going on to like public networks and doing a bunch of random stuff. All right, so number 3, we have the network layer with IP spoofing, Smurf attacks, and hijacking attacks. And IP spoofing is when you're faking an IP and you're pretending to be someone who you aren't, and then you can pretend you're a client, and then they'll send you information that shouldn't be sent to you. And that's kind of similar to a hijacking attack, where a client connects with a server, and then they have a good connection, and then you hijack their connection, you take their IP, and then you're now trusted. And so Smurf attack. All right. I kind of blinked out on these, not gonna lie. All right, so Smurf attack is like when, oh, okay. So Smurf attacks, basically you take, all right. Okay, so, okay, actually, I'm not too sure on these, and we're kind of low on time. So you guys can Google these yourself, but these are kind of some of the attacks that exist on the network level. And I'm pretty sure Smurf attack is, all right, okay. It can be considered a denial of service attack, and basically you're just sending a ton of data to a server trying to flood it and prevent it from operating normally. And so you can kind of protect these things with having secure routers and firewalls. So making sure you're filtering the packets so you don't get an overload in packets, and the IP addresses you're connecting to, or IP addresses that are bad, are blacklisted or put on a list saying, no, you can't connect to these, or whitelisted where they're definitely good. Okay. And so for layer 4, it's TCP and UDP flooding. So layer 4 is the transport layer. And so this is kind of tied into network layer, and network layer and transport layer sometimes kind of intermix. But this is where you can have TCP and UDP packets are getting sent, and if there's overload, then you get DDoS attacks, and there's also SYN floods where you basically, a client connects to a server, and there he's waiting on a handshake, but and waiting on that 3-way handshake, but it waits out and times out, and it kind of just fills up all the spots, and you can basically slow down a computer like that. And so basically all these attacks are actually the best line of defense is making sure your server and whatever is configured correctly, and making sure you're conservatively accepting requests, and making sure that even if people can communicate to you, you can make sure to adapt to if there's like potential bad guys. All right, and then SYN cookies are a way to protect SYN floods, because usually what happens with a SYN flood is actually, dude. All right, I kind of blinked out on all this. All right, so yeah, so SYN flood is when you're waiting for a connection, and okay, I'll just move on. But you guys can definitely search it up online and then read about it. There's great articles on it. And so for 5, 6, and 7, those are more of the application side, and for the application side and more of your own computer and software. And so you can have DDoS attacks on both layer 3 and 4 as well as 7. And so DDoS attacks on 7 are attacking through protocols like HTTP, or mainly HTTP. And while layer 3 is just like just sending data and pure data, and or not pure data, but it's sending data on that layer and through IPs. And it's like kind of, yeah. All right. And with the defense for these kind of things, there's a bunch of services and they offer real-time protection. You have Cloudflare, Cloudflare, you guys might have heard of it before, but they kind of use real-time responses and they try to handle these attacks. Although it's pretty difficult because it can be coming from all around the world through a bunch of different computers, they try to do their best and use secure policies and kind of prevent overload or attack. And yeah, I think that's basically it for network security. And I think that's about it. I'll get back. I'll definitely put in the Discord on SYN floods and things I've missed out on man in the middle attacks. But that's basically it for networking. And if anyone has any questions, they can put in the chat, or if any questions pop up in the future, you can email us or message us on Discord or anything. And we also have our social media platforms open.